Hello statistics students, Miss A here. So I'm going to be going over in this video about Unit 1 Lesson 6, where we're going to learn a few different ways to determine some information about not only where is this value, but where is this value relative to all the other values in the distribution. And let's see kind of what that means. All right, skip over Zoom etiquette. So we're going to need to be thinking now about this idea of relative position. So let's use an example. We have Javon and Amir, and they're high school basketball players, and here's the scores for their first 20 games. For Javon, we can see that his scores are kind of a little bit all over the place, right? He had a game with 0 points and 6 points and 8 points and went as high as 24. Whereas Amir seems much more consistent, right? He's never scored less than 13, but never scored more than 20. So, right, two very different types of players. But last night, both of them scored 17 points. So who is that a better game for? If you're having trouble conceptualizing that question, use a more extreme example. Think about me as a basketball player versus LeBron James. If I scored 17 points in an NBA game, it would be an absolute miracle. It would be the biggest miracle ever. It would be an amazing game for me. For LeBron James, it's mediocre. We can think about heights of people. So for instance, say we have someone who's 6 feet tall, or let's make it even more. Say someone who's 6'8", right? If you see a person who's 6'8", on the subway or on the street or in the store or whatever, that person's going to seem really, really tall. Whereas if that person is in the NBA, they're actually probably on the shorter side. So where they come in their distributions is going to be very, very different. So let's get back to this game example, right? So 17 games, how good of a game is that for Javon? How good of a game is that for Amir? Let's see if we can put some numbers to it. So, right, again, this is so we need to rephrase the question a little bit to put this into terms that math can deal with, right? So if we're asking, say, how good of a game did Javon have, we can rephrase that and ask, well, what percentage of his games is this better than? Is 17 points better than half his results? Is it better than all of his results? Or is it maybe only better than 1 or 2 results? Maybe it's close to the bottom of his list. So we want to think of it this way, right? What percentage of Javon's games is this as good or better than? Or we can think, right, what percentage of his games are that good or worse? How many games out of his 20 did he score 17 or fewer? And then we can say, well, this 17-point game was better than that percentage. So we can highlight that here, right? So I went ahead with Javon, I highlighted in yellow, and Amir, I highlighted in purple. The yellow is going from 0 up to 17 for Javon. And we notice, right, he had 2 games of 17, and I included both. So we're asking what percentage of games did he score that many points or worse? So we're thinking, right, this new 17-point game was better than that percentage, right? So 13 out of his first 20 games, he scored 17 points or less. So we can say that his current game, right, this last game that he played last night where he scored 17, is as good or better than 65% of his games. So, right, so about 2/3 of his games are that good or worse, and about 1/3 of the games are better. So, it's better than half of his games. But now let's look at Amir. Right, Amir is a much more consistent player. He's like never scores that little, but he also doesn't tend to score a lot. So actually it's fairly rare for him to score 17 points, right? 18 out of his first 20 games were 17 points or fewer. That means only 2 of them were better than 17. In contrast to Javon, where 7 of his games were better than 17. So really, it's kind of funny to think, like, if you just look at the numbers originally and you see that 0 and the 6 and the 8 and the 9 for Javon, and you're like, oh, well, compared to that, the 17 is pretty great. But really, it's only better than about 2/3 of his games, and it's worse than the other third. Whereas with Amir, he very rarely does better than 17. So actually, this is a very good game for Amir. It's an excellent game for Amir. It's like an above average. It's a pretty decent game for Javon. And we get this by thinking about this relative position in their distributions, right? I only compared Javon's game to all of Javon's games, and I compared Amir's game to Amir's game. I did not compare them against each other. So what we just found is called the percentile of the value. And this is telling us, right, what percentage of values in that distribution are at that level or worse. The SAT is a very common place that you end up seeing this. When you get your score report, they will tell you you scored in the 87th percentile. That means you scored as well or better than 87% of other test takers. So you did really well. That means only 13% of test takers did better than you. The other place that we tend to see this a lot is, say, if you've had a kid, or if you know anyone who's had a kid and had to go to like a pediatrician's appointment, especially for a baby, they'll have these charts in their office showing you like what percentage of babies are like at this height by this age. And so you can kind of see, so you can tell, my kid is 1 year old and weighs 10 pounds. And the doctor might say, okay, your kid is at the 74th percentile for weight. That means that this kid is as heavy or heavier than 74% of kids their age, but that means they're also less heavy than 26%, right? The complement that would add us up, that would get us up to 100%. So this is how we interpret percentiles. And a really common way that we visualize these, again, say for instance that example of the birth weight or the weight chart that a pediatrician might be using, is going to be an example of this, what we call relative cumulative frequency graphs. So what does all of that mean, right? So relative frequency, we know that. We studied that when we did categorical variables. And what relative frequency means is like what percentage of the distribution are like at that value. The cumulative part means that we're kind of starting at 0. We're basically saying, okay, as we go up. So for instance, here we might say, what percentage is at 160 pounds or lower? Or we might ask, how, like, if a person is at the 67th percentile for weight, that means that they are heavier than 67% of their cohort, then we can kind of get that information from here. So here in this example, right, again, we're using this example of the 67th percentile. And so we look at the y-axis and we go for 0.67. So this is telling us, right, this is the value where 67% of the distribution is below you. That's why as we go from left to right, the graph is always more or less going to be going up, because more and more of our distribution will be swept up in this. So say for instance, at 140 pounds, you're like not even heavier than 5%, right? There's probably only about 2 or 3% of people who are less heavy than you. For like so, right, if we're kind of looking here at 140. When we get up to 150 and we kind of, right, we go to 150, we go up, and then we go across to the y-axis, it comes in at a little less than 20%. When we get up to 160, right, we go up and we go across, and we're getting close to about 50%. And what do we call that point where 50% of the distribution is below you and 50% of the distribution is above you? The median. So if we look for the 0.5 on the y-axis and we go over to the curve and then we go down, that will tell us the median weight for the distribution. And you can go either way. Say with what's appearing on this graph here, we could ask what percent, if a person weighs 160 pounds, what percentile are they at? Okay, 160, you go up, and we said it's like close to 50%. We'd say it's maybe like the 48th percentile, 49th percentile, somewhere close to 50. So they're heavier than about half the group. They're less heavy than about half the group. But then I could ask, for instance, say, okay, if I were to pick someone at the 67th percentile, how much would they weigh? Or we could ask, so the lightest, the least heavy 67%, so about 2/3 of these people weigh how much or less? So we could say, well, 67% of these people weigh, this looks like about 165 pounds or less. And of course, that leaves us with 33% on the other side who would be heavier. We're going to use these graphs quite a bit, so we'll get a lot more practice reading them. But for right now, let's look at a different way of looking at relative position. Or actually, sorry, first, let's practice. Okay, so we got 3 percentile problems. The first one is a fairly clear-cut one, like I just did. Number 2, you're gonna really read the question. Make sure you're answering what it's asking. And with number 3, right, we're actually gonna have to use this table of data to get it. So you might wanna look a few slides back to figure out how to do that. So again, please complete this in PearDeck so that I can see your responses. Please let me know if you have any questions. So let's move on to Z-scores. So Z-scores are a really nice way of showing relative position when, say, we don't have all of the data at our disposal. Like, what if I'm just going online and I look up what is the mean height for adults in the United States, or what is the mean income? Right, if I can only find the summary statistics, right, I can't get all that data, I can just get the summary, then Z-scores are a great way to go because you can find them solely based on the mean and the standard deviation. If you know those two things, you can get the Z-score. You don't need a fancy relative cumulative frequency graph, you don't need actual data, you just need those two statistics. So, Z-score is a way of measuring deviation. You can look at the numerator here, right? We take a value and we subtract the mean of the distribution. That's simple deviation. How far is this point from the mean? And then, though, we're gonna kind of think of it a little differently. Sort of like you might have heard people talk about distances or lengths in terms of football fields. They might say, this factory is 5 football fields long, right? We're gonna do something very similar here, only instead of a football field to measure distance, we're gonna use the standard deviation to measure distance. This came up the last lesson, if you remember, when we were talking about doing a 3 standard deviation test for outliers, right? We started at the mean and we went up or down by 3 standard deviations. So we already have kind of seen using the standard deviation as a unit of measure. Here, we're really baking that into the process by making it part of the formula. So how do we put this in terms of standard deviation lengths? by dividing by standard deviation. So we take whatever our simple deviation was, value minus mean, we divide it by standard deviation, by like the size of the standard deviation, and then we get this measure of how far from the mean is this point in units of standard deviation. So we could say this point is 1 standard deviation away, this other point is 1.4 standard deviations away. So it gives us a lot of nice detail there. And again, it's easy to calculate because you only need 2 very common statistics. Mean and standard deviation are 2 of the most common things you'll find reported about any distribution. So generally it's very available and it's easy to use. Who doesn't love that? So let's kind of look at Javon and Amir again. So now we're going to look at their rebounds. So Javon, as a statistics student, has kept track of all of his games and he's compiled data about his rebounds. So his mean number of rebounds per game is 8, and it has a standard deviation of 2 rebounds. So that means like 2/3 of his games have somewhere between 6 and 10 rebounds in them. For Amir, he's done something similar. He finds out that his mean number of rebounds per game is 5 with a standard deviation of 3. So he's got a lower mean and higher standard deviation. Whereas Javon, right, he's got the higher mean and lower standard deviation, right? He's a much more consistent rebounder, unlike with the points. So last night, they both, right, somehow last night, they had these very similar games, right? 17 points, and they both had 7 rebounds, okay? So let's look at it for Javon. Okay, 7 rebounds is 1 below the mean. So the deviation would be 1 rebound. It is, and specifically -1, because it's 1 rebound below the mean. And if his standard deviation is 2, then 1 divided by 2 gives us that this is half a standard deviation below the mean. So you would have a Z-score of -0.5. For Amir, he got 2 more rebounds than he usually would. And 2, if we take a deviation of 2 rebounds, divided by the standard deviation of 3 rebounds, 2 divided by 3 gives us 2/3. So his Z-score would be positive 2/3 or 0.667 if we're stopping at 3 decimal places. So this is how we find the Z-score. First, you find that simple deviation, how far above or below the mean is this value, and you divide by standard deviation to put that deviation in terms of standard deviation lengths. So, right, so Amir was 0.667 standard deviations above his mean. Javon was half a standard deviation below his mean. And this is really nice because, like that first example with percentiles, this lets us compare their performances relative to their distributions, right? A higher Z-score means it's a more exceptional performance. So Amir, once again, did better relative to himself. He was 2/3 of a standard deviation above his mean. Javon was half a standard deviation below his mean. If anything, right, that's a bad performance for Javon. Again, even though they have exactly the same number of rebounds for the value, 7. So again, we always want to be doing these things in terms of that specific distribution. If we're talking Amir, we use Amir's mean and Amir's standard deviation. If we're talking about Javon, we use Javon's mean and Javon's standard deviation. We do not mix and match. The whole idea is we are comparing someone to the rest of their distribution to figure out, relatively speaking, how good or bad was this, or how exceptional was this, right? The more standard deviations away we go from the mean, as we might remember from the last lesson about outliers, More standard deviations out means more exceptional, more unlikely, more extraordinary, whatever you want to call it, but it definitely, like, the further out you go, the less and less, or the more and more it's going to stick out from the rest of the data. So we once again come to another practice. Again, I want you to do this in PearDeck so that I can see your answers and leave you some comments. Here we're going to have like kind of an interesting setup. We have Pablo and Preeti, and we have some summary statistics about their travel times, their commute times in the morning. Pablo's is mean of 46 minutes, standard deviation 5 minutes. Preeti commutes a mean value of 58 minutes with a standard deviation of 8 minutes. So if we go back a few slides here, use this formula. Take the target value, subtract the mean of that distribution, then divide the result by the standard deviation. And this will give you the Z-score. So, and I'll leave it here by highlighting question number 3, where we are comparing Z-scores. So remember, larger Z-scores, either in the positive or the negative direction, right? More standard deviations means more exceptional. To go back to the Javon and Amir example, not even thinking about direction, above the mean or below the mean. Amir's value is 2/3 of a standard deviation from his mean. Javon's is half a standard deviation from his mean. So Amir had a more exceptional game, right? 7 is not a number of rebounds he will get very often. Whereas for Javon, 7 is an amount that he gets. Like, it's still fairly close to his mean. It's well within his normal window, much more so than for Amir. So for number 3 in this practice, don't think so much about the sign. Just think about the size of the Z-score. Whose score shows more standard deviations distance from the mean? Whichever one has more standard deviations difference is going to be the more exceptional value. Okay, so that's it for Unit 1, Lesson 6. Again, you can find links to the PearDeck slides on Google Classroom. You can find the assignments on Google Classroom. You can find the textbook on Google Classroom. Please let me know if you have any questions about any of this. Leave a comment, send me an email, whatever you feel like doing. But otherwise, have a wonderful day.